so now we're ready to look at the next level of reaction stoichiometry problems. What makes these problems different? So if we read through this, we see that they've asked us to calculate the mass of sodium metal. So we're specifically looking to solve the mass of this guy. In addition, they gave us the mass of chlorine gas. So this was given. And that's different because before it was just all about the moles. Now we're going to have to take some extra steps. First, we're going to have to convert the mass to moles. When you balance an equation, those numbers out front are mole to mole conversion factors. You can't use them with masses. You have to do that conversion first. So a couple things before we actually set up the problem. First, we're going to need to balance our equation. So I have 2 chlorines here, and I'm going to put a 2 out front here. That gives me 2 chlorines, but it also gives me 2 sodiums. So I'll put a 2 there, and then there's a 1 that's understood in front of my chlorine gas. Sodium metal is just a monoatomic solid. So I could just grab the molar mass directly from the periodic table. However, the diatomic chlorine, I'm going to want to calculate that molar mass ahead of time. So off in the margin somewhere, it's 35.45 for 1 chlorine, but it comes out twice. So we're looking at 70.90 grams of Cl2 per 1 mole of Cl2. So that's going to be a handy conversion factor that'll get us to the moles. Starts with the number they gave us. That part is still the same. And then moles is the bridge to wherever we want to go. So let's get those grams to moles. So I'm trying to get rid of grams. And I'm trying to go to moles of diatomic chlorine. Your molar mass is always going to have the number 1 with it. It doesn't matter what the coefficients of the balanced equation are. Molar mass always has the number 1. So I'll have 1 mole of chlorine has 70.90 grams of that chlorine gas. For me, it's helpful. I like to look at stuff and see how stuff is canceling while I'm setting it up. So I got rid of grams of chlorine. Now I'm in moles of chlorine, and that's a familiar position to be in from yesterday, right? So I want to get rid of moles of chlorine. And I'm interested in the moles of sodium. So when you're changing from one thing to another, you're going to set up that mole to mole conversion factor. So we're going to do 1 mole of chlorine is associated with 2 moles of sodium. I wrote them in pink just to emphasize that these values were grabbed from here. This cancels, and now I'm left with moles of sodium. They want me to report the mass of sodium. So I'm going to get rid of moles of sodium. And since it's a molar mass, I'm going to use the number 1. Always use 1 molar mass. And it's around 23 grams of sodium in 1 mole of sodium. So that last one cancels nicely as well. And I'm left with grams of sodium. So in your calculator, you're going to want to multiply 241 times 2 times 23. Usually at that point, I hit enter. And then we're going to divide by 70.90. And I'm going to use 3 sig figs. So I got 156 grams of that solid sodium metal at the end of the day. All right, so for our next problem, we're given the fact that we have 61.7 grams of C3H6, and they asked us to calculate the mass of carbon dioxide. Since both of those values have grams associated with them, I'm thinking in the back of my head, I need to convert them to moles, and I'm gonna need the molar masses of carbon dioxide and the C3H6. So let me go ahead and calculate that. So the coefficient doesn't matter when you're calculating the molar mass. So here, I'm going to ignore this 2 of the balanced equation, and the problem told us it's already balanced, so it's nice of them to do that. I'm going to ignore this 2 and just focus on the C3H6. So I have 3 carbons, so 12.01 times 3. Grams in there, and 6 hydrogens. So 1.01 times 6. If you have slightly different values using a different periodic table, it's okay. We'll pretty much get the same answer in the end. For that one, I got 42.09 grams. And it's going to be of C3H6 per 1 mole of C3H6. So here's one powerful conversion factor that I'm definitely going to need to use. Let's do the same for the carbon dioxide. So carbon is 12.01 and 2 oxygens. So that's 16 times 2. So with carbon dioxide, I'm looking at 44.01 grams of CO2 per 1 mole of CO2. I can't emphasize this enough. Molar masses always go with 1 mole. It doesn't matter that there's 6 moles in the balanced equation. We don't use that in the molar mass part. So start with what they gave us, 61.7 grams of C3H6, and there's 42.09 grams of C3H6 in 1 mole of C3H6. So I'm just using this conversion factor that we got from the molar mass. Grams of C3H6 cancels with grams of C3H6. Now I want to get the moles over to the moles of carbon dioxide. So I'll put moles of C3H6 on the bottom and moles of carbon dioxide on top. When you're going from moles of one thing to moles of another, that's when you pull your coefficients of your balanced equation. So I'm going to put a 6 in front of the carbon dioxide and a 2 in front of the C3H6. Now we've gotten rid of the moles of C3H6, and our last step here is going to be to get rid of the moles of carbon dioxide and turn it into grams of carbon dioxide. So 1 mole of carbon dioxide has that 44.01 grams. So I'm just left with grams of carbon dioxide. When I plug this into my calculator, I would do 61, I'm just going to write the value, 61.7 times 6 times 44.01. And you're going to either want to press enter at that point or use a big set of parentheses around the whole thing. And then when you divide, since there's more than one thing going on underneath, use parentheses. So you're going to divide by 42.09 times 2. Sometimes if students are having difficulties with their calculators, you're like, I'm plugging it in, I'm not getting the same answer, then I'd recommend multiplying everything across the top, writing down your answer, multiplying everything across the bottom, writing down your answer, and then dividing after you've multiplied the top and the bottom. But it's easier this way, so, I mean, it's faster this way, not necessarily easier, but it's faster this way, so try to do it this way. Here I got 193.54 grams of carbon dioxide. However, looking back, we only have 3 sig figs with this number, so I'm going to round this to 3 sig figs and say that there's going to be 194 grams of carbon dioxide produced by this combustion reaction. So for this problem, I took care of a couple things ahead of time. Since they gave me the 250 grams of copper, I grabbed the atomic mass of that off the periodic table and set up my conversion factor. Likewise, since we're solving for the mass of gaseous sulfur dioxide, that's what they want us to find, I knew I would need the molar mass of that species as well. So I went ahead and calculated that. I checked that my equation was balanced, and it was, and it happens to have all coefficients of 1. Let's start with the number they gave us. So 250 grams of copper. And then since I'm using my molar mass first, I'm going to write that 1 mole of copper has 63.546 grams of copper. And so grams of copper cancel with grams of copper. Now 1 mole of copper and this one, just to emphasize it, is from my balanced equation. So 1 mole of copper is gonna correspond to the formation of 1 mole of sulfur dioxide. So I've established that ratio from my balanced equation. And then my last step here would be to convert the moles of sulfur dioxide to grams of sulfur dioxide. So I'm using my molar mass, so 64.07 grams of sulfur dioxide. Let me just take a second and check my units, make sure everything's set up properly. Moles of copper, cancel with moles of copper. Moles of sulfur dioxide, canceling with moles of sulfur dioxide. And I'm left with grams of sulfur dioxide. And when I solved this earlier, I got 252 grams of sulfur dioxide. So here we're asked to solve for the mass of magnesium oxide that can be dissolved by 121 grams of nitric acid. I made sure the equation was balanced, and I also preemptively calculated my molar masses for magnesium oxide and nitric acid. They're over there in the corner. So I'll start with 121 grams of HNO3. And then I'm going to say 1 mole of HNO3, because it's my molar mass, I'm using 1, contains 63.02 grams of the nitric acid. At this point, I'm going to set up that mole to mole conversion factor and turn the nitric acid into magnesium oxide. So I'm thinking I want to get rid of moles of nitric acid, so I'll put that underneath. Moles of magnesium oxide on top. And then there's a 1 out front here. And a 2 out front here. So moles of nitric acid cancel with moles of nitric acid. And my last step will be to use the molar mass of magnesium oxide to get that into grams. So 1 mole of magnesium oxide has 40.31 grams. I got an answer of 38.698 grams of magnesium oxide. However, looking back, I have 3 sig figs, 4 sig figs. These are exact 4. So I only have 3 sig figs for my answer. So I'm going to report my final answer as 38.7 grams of magnesium oxide. Those units are really important too. Here, let's read through this and really try to see what they're asking us for. It says calculate the mass of NH3. So we want the mass of the NH3, and I'll underline it over here too, that can be prepared by heating 2.50 moles of solid ammonium carbonate. So it's balanced, and I got the molar mass of ammonia. This one, we're going to start with 2.50 moles, because that's what they gave us. So remember, moles is your bridge to wherever you want to go. We're already in moles. We don't need the molar mass of this because we already have moles of it. So I'm going to just get rid of the moles of ammonium carbonate, put it in the denominator so it cancels out. And then since we want the mass of ammonia, I'm going to put moles of ammonia in the top. So again, if you're given moles to start, then you don't really need the molar mass. There's a 1 out front there, and a 2 out front there. So I'll do a 2-to-1 ratio on that conversion factor. If I ended my problem right now, I'd be in moles of NH3, but they did ask me for the mass of NH3. So let me add 1 more conversion factor. I'm going to say 1 mole of ammonia. I'm using moles. I'm using molar mass, so I need to do 1 mole. Has 17.04 grams of ammonia. This cancels with this, and we're left with grams of ammonia. So for this one, I wound up getting 85.2 grams of ammonia. Alrighty, so first things first, we have an unbalanced equation. So I'll take care of that. There's 2 oxygens here and 2 oxygens here. So I know that I can only go by 2s, 2, 4, 6, 8. Here we have 3 oxygens. So ideally, I need to turn the 3 into an even number, right? And so I'm going to accomplish that by putting a 2 out front here. Now I have 6 oxygens and 2 sulfurs. Let me fix my sulfurs. I'll put a 2 out front over here. So I have 2 sulfurs. 2 times 2 is going to give me 4 oxygen, plus another 2 from here, and that's 6 oxygen. So I have 6 oxygen and 6 oxygens, 2 sulfurs and 2 sulfurs. It looks balanced. Again, really focusing and honing in on what they're asking us for. It says, calculate the number of moles of oxygen gas. So moles of oxygen gas required to convert 17.5 grams of sulfur dioxide. So I'm going to start with this value. And this is just like extra description. Yeah, we make sulfur trioxide, but we don't need that information to get the answer. All right, so I'm going to start with 17.5 grams of SO2. And I'm going to pull, I did it earlier, I'm going to pull the molar mass of SO2 to set up that conversion factor. Now that I'm in moles of SO2, I can pull my coefficients from my balance equation and convert moles of SO2 to moles of oxygen gas, because they want us to get moles of oxygen gas. So I'll get rid of moles of SO2 and go to moles of O2. Let's grab those coefficients. So I got a 2 there and a 1 there. Moles of SO2 cancel with moles of SO2, and I'm going to stop with the conversion factors because they don't want mass. This time they want us to get moles of SO2. So 0.136567 moles of O2. 3 sig figs, 4 sig figs, exact numbers. I'm going to report my final answer as 0.137 moles of O2. So first things first, let's check if the equation that they gave us is balanced. And looking at this, we got 1 potassium over here, but 2 potassiums over there. So that's not balanced. It is an acid-base neutralization reaction. We have that clue in the prompt itself, but also you might recognize the sulfuric acid, and then we have a base, and it's producing water. When I balance acid-base neutralization reactions, I find it helpful to think of the water as being HOH. So when counting things in an attempt to balance, I keep the OH together, kind of like the hydroxide. So I'm going to ignore this for like just a second. We'll put it back. We'll fix it in a second. So the hydroxide is clumped together. The other thing that I see that I can kind of keep as a group is the sulfate. So I'm going to put a green cloud around the SO4. So let's see. 1 potassium, 2 potassiums. I'll put a 2 out front here. Now I have 2 potassiums, that's okay, and 2 hydroxides. I'm going to need to put a 2 out in front of the water to get the 2 hydroxides. That in turn gives me 2 hydrogens. I'm not double counting the ones that belong to the hydroxide, so just 2 H's. But I have 2 H's over here. 1 sulfate and 1 sulfate. So it's balanced like this. I'm going to put a 1 here, and there's a 1 here, and I'll fix this. The water needs a 2 in front of it. And we're all set. We can start doing our actual problem now. So at the end of the day, they asked us to solve for the moles of KOH. We started with 29.7 grams of sulfuric acid. Grams are pretty useless. They're only helpful in the actual lab, right, when we can mass stuff. We need to be in moles for most of our work. So use my conversion factor. Remember, I'm going to put 1 mole of sulfuric acid because this is a molar mass. Never ever look at the coefficients when you're doing your molar mass. Sulfuric acid cancels sulfuric acid. Now I want to get rid of moles of sulfuric acid and turn it into moles of potassium hydroxide. Now I can grab the coefficients of the balanced equation. See how things are canceling? The moles of sulfuric acid's gone now, and I'm just left with moles of potassium hydroxide. When I did this earlier, I got 0.606 moles of potassium hydroxide.